All right, welcome. Today, we are diving deep into two of the absolute cornerstone ideas in all of linear algebra, basis and dimension. You could really think of these as the fundamental building blocks, kind of like the DNA that lets us understand and work with vector spaces.
So, let's kick things off with a big, kind of mind-bending question. Vector spaces, they're these massive, often infinite places with countless points. So how in the world can we get a handle on something that's infinite using just a small, finite set of rules? That's the puzzle we're going to solve today.
And here's our game plan. First, we're going to figure out how to tell which vectors are essential and which are just extra fluff. Then we'll see what we can actually build with the essential ones. After that, we'll combine those two ideas to define what a basis really is, get a real grip on dimension, and finally, see why this whole concept is so incredibly powerful.
Okay, first things first. We need to learn how to separate the signal from the noise. How do we spot the vectors that give us brand new, unique information versus the ones that are just kind of repeating something we already know? It's all about finding what's truly essential.
This right here is the core difference. On the left, you've got linearly dependent vectors. Think of them as redundant. One of them is just a mix of the others, so it's not adding anything new. But on the right, linearly independent vectors are the essential ones. Each one brings a new direction to the table. And there's a really clean test for this. The only way to combine them and get back to the zero vector, back to where you started, is if you basically don't use them at all. All the scalars have to be zero.
Let's picture this, because it makes it so much clearer. If you have two independent vectors, they have to point in different directions. They break free and open up an entire plane of possibilities. But if they're dependent, they're trapped on the same line. One is just a stretched out or shrunken version of the other. It doesn't give us a new direction to explore.
So, we figured out how to pick out our essential non-redundant vectors. The next logical question is, what can we do with them? What kind of universe can we build using just these pieces?
And this leads us to the idea of a span. The span is really just the collection of all the points you can possibly reach. It's every destination you can get to by stretching your vectors, shrinking them, adding them together, basically mixing them in every possible way. If your vectors are ingredients, the span is every single dish you could ever hope to cook.
And here's a really crucial point. The span isn't just some random cloud of points. It's a complete, self-contained world. If you take any two vectors inside that span and add them, the result is still inside the span. It follows all the rules. It forms its own perfect little vector space.
All right, time to put it all together. We've talked about essential independent vectors, and we've talked about what those vectors can build or span. Now let's combine those two powerful concepts to define the perfect, most efficient toolkit for building any vector space.
And here we have it, a basis. For a set of vectors to be a basis, it has to meet two really strict conditions. First, the vectors have to be linearly independent, no redundancy. Every single one is essential. And second, their span has to be the entire space. They have to be powerful enough to build absolutely everything. It's that perfect sweet spot. Maximum efficiency, total coverage.
Now this uniqueness, this is the superpower of having a basis. What it means is that for any point in your space, for any vector you want to get to, there's one and only one recipe for how to build it using your basis vectors. It's like a unique address. There's zero ambiguity. But hey, how can we be so sure this is always true? Well, we can actually prove it, and it's pretty slick. Let's walk through it. Let's just pretend for a second that you could have two different recipes to make the same vector. Okay, so if you subtract one recipe from the other, the answer has to be the zero vector, right? But look what that gives you. It gives you a way to combine your basis vectors to equal zero. But wait a minute. We already know basis vectors are linearly independent. The only way to mix them up to get zero is if all their coefficients are zero. Which means those two different recipes we started with, they had to be the exact same thing all along. The uniqueness has to be true.
Now, all of this elegant structure leads us to something that sounds really complex but is actually shockingly simple. It gives us a way to count the size of an infinite space.
And this is where it gets really amazing. A single vector space can have an infinite number of different bases. You could pick your standard x and y axis or some totally weird skewed vectors. But, and this is the incredible part, no matter which valid basis you choose for a space, it will always have the exact same number of vectors. That number is a constant property of the space itself.
And that constant, unchangeable number? That gets a special name, the dimension. That's all it is. So when we say that a plane is two-dimensional, what we're really saying, in the language of linear algebra, is that any basis you choose for that plane must have exactly two vectors. It's just counting your building blocks.
So, after all this theory, you might be wondering, okay, so what? Why does any of this matter? Let's talk about the payoff, because this is one of the most practical and powerful ideas in all of math and data science.
Here's the huge payoff. Think about a linear transformation. You know, some operation that rotates or stretches or squishes an entire space. That space has an infinite number of vectors in it. How could you possibly track what happens to all of them? You can't. It's impossible.
Well, you don't have to. You only need to see what that transformation does to your handful of basis vectors, just those few. Because every other vector in that entire infinite space is just a unique recipe of the basis vectors, if you know where the basis goes, you can calculate with perfect precision where every other vector goes. This is the magic. A basis lets you take an infinite problem and make it finite. It's an incredible, powerful shortcut.
And that leaves us with a final fascinating question to think about. We know any space has infinitely many possible bases. That means the basis you choose to use really matters. It's like putting on a different pair of glasses. The right choice can make a hard problem suddenly seem easy, or can reveal hidden structures you never knew were there. So the real question is, what does your choice of basis tell you about the world you're trying to understand?